Recall that an nth order initial value problem is a problem of the form a sub n of x dny over dxn plus an minus 1 of x dn minus 1 of y over dxn minus 1 plus so on and so forth plus a1 of x dy dx plus a0 of x times y is equal to g of x with the conditions y of x naught equals y naught, y prime of x naught equals y1, so on and so forth, y n minus 1 of x naught equals y sub n minus 1. So when does this have a guaranteed solution? So we're going to let an of x, an minus 1 of x, so on and so forth, a1 of x, a naught of x, and g of x be continuous on the interval I. We will also let an of x not be 0 for every x in this interval I. If x equals x naught is any point in I, then a solution y of x of the initial value problem given above exists on the interval and is unique. So we saw how to solve an initial value problem of first order. We're going to look at solving an initial value problem of a second order. So we're going to consider the initial value problem y double prime minus 4y is equal to 12x with the conditions that y of 0 is 4 and y prime of 0 is 1. We're going to verify that y of x equals 3e to the 2x plus e to the minus 2x minus 3x is a solution to this differential equation. Then we will use, we're going to verify that this is a solution to the entire initial value problem. Then we will try and determine the largest interval for which it is the unique solution. So, if this is y, then y prime is 6e to the 2x minus 2e to the minus 2x minus 3, and y double prime is 12e to the 2x plus 4e to the negative 2x. So y double prime minus 4y, this would be 12e to the 2x plus 4e to the negative 2x minus 4 times 3e to the 2x plus e to the minus 2x minus 3x. So this equals 12e to the 2x plus 4e to the negative 2x minus 12e to the 2x minus 4e to the negative 2x plus 12x, which is equal to 12x. So this function satisfies the differential equation. We now must check that it satisfies the initial conditions. So y of 0, we get 3e to the 0 plus e to the 0 minus 0, which is 3 plus 1, which is 4, so that checks out. Y prime of 0 is 6e to the 0 minus 2e to the 0 minus 3. This is negative 5 plus 6 is 1, so that checks out. So this function satisfies the initial value problem, and so it is a solution to the initial value problem. Now we have to try and determine the largest interval for which it is a unique solution. The condition in which this is a unique solution, remember, is that each of the coefficients must be continuous on the interval, and the leading coefficient has to be non-zero. So for this problem, our a2 of x is 1, our a1 of x is 0, our a0 of x is negative 4, and our g of x is 12x. Now, 1 will never equal 0. And furthermore, these are all continuous on any interval containing x equals 0. So I should specify this is not equal to 0 for all x. So this says that any interval that contains 0, this would be the unique solution on that interval. So the largest such interval would be all real numbers. Another common type of problem when dealing with higher order differential equations is a boundary value problem. Or a BVP. For linear differential equations, it'll have the form an of x dny dxn plus a sub n minus 1 of x dn minus 1 y dx n minus 1 plus so on and so forth plus a1 of x dy dx plus a0 of x y is equal to g of x, given the boundary conditions alpha 1 y of b1 plus beta 1 y prime of b1 plus so on and so forth plus gamma 1 times the nth derivative of y, value of b1 is equal to delta 1, alpha 2 y of b2 plus beta 2 y prime of b2 plus so on and so forth plus gamma 2 yn of b2 is equal to delta 2, so on and so forth, and the final alpha n y of bn plus beta n y prime of bn plus so on and so forth plus gamma n yn of bn is equal to delta n, where each of the alphas, betas, gammas, and deltas are constants. All of these values, or these conditions, are called the boundary conditions. Now, unlike an initial value problem, boundary value problems can be really difficult to solve. For purposes of this course, we will really only be considering initial value problems. Let's look at the differential equation x double dot plus 16x is equal to 0. Now, we've already shown that the function x of t equals c1 cosine of 4t plus c2 sine of 4t is a solution to this differential equation. We will now look at 3 different boundary conditions and try and find c1 and c2. So the first boundary condition, x of 0 equals 0, x of pi over 2 also equals 0. So under this boundary condition, x of 0, well, we're going to have c1 cosine of 0 plus c2 sine of 0. Cosine of 0 is 1, sine of 0 is 0, so this is just c1, and this has to equal 0. So x of pi over 2, we get c1 cosine of 4 times pi over 2, which is 2 pi, plus c2 sine of 4 pi. This just equals, again, c1. From above, that has to be 0. And the condition is this has to be 0. Well, this would imply that c2 can be any real number. So our solution would be x of t equals an infinite number of solutions. So it's any solution of the form r times sine of 4t such that r is a real number. Let's now consider the boundary condition given by x of 0 equals 0 and x of pi over 8 equals 0. and we do the same thing. So x of 0, I'm not going to reinvent the wheel from above. This is C1, which has to be 0. X of pi over 8. So we get C1 times the cosine of 4 times pi over 8, which is pi over 2, plus C2 sine of pi over 2. Cosine of pi over 2 is 0, sine of pi over 2 is 1, so this is just C2, and that has to equal 0. So for this boundary condition, C1 has to be 0, and C2 has to be 0. So now we have a single solution. The only solution is x of t equals 0. The third boundary condition we'll look at, x of 0 is equal to 0, and x of pi over 2 is equal to 1. Well, again, from above, x of 0 equals 0. I'm sorry, x of 0 is C1, which has to be 0. X of pi over 2, once again, from the first boundary condition, is also C1. Which from above is 0, but the boundary is supposed to be 1. Well, this says that 0 is equal to 1. This is nonsense. This is a contradiction. This means that this boundary condition has no solution. So we've seen now that depending on the boundary conditions, we have 3 possibilities. We can have an infinite number of solutions. We can have a single solution, or we could have no solution. Consider the linear differential equation given. Recall that if g of x is identically 0, then we say that this is a homogeneous linear differential equation. Otherwise, it is said to be non-homogeneous. Another way we could write this differential equation is by using the differential operator. Which is d. Using this, the above equation can be written as an of x d to the ny plus a sub n minus 1 of x d to the n minus 1 y plus so on and so forth, plus a1 of x times dy plus a naught of x times y is equal to g of x. Or we could factor out the y, and I use the word factor lightly. So we could also write this an of x times d to the n plus a n minus 1 of x d to the n minus 1 plus so on and so forth plus a1 of x d plus a naught of x y is equal to g of x. This notation is very useful when studying the theory, as we will now see. So this is known as the superposition principle. Specifically, this one is for homogeneous equations. And what it says is if y1, y2, yn are solutions of the homogeneous linear nth order differential equation on an interval I, then the linear combination given by y equals c1y1 plus c2y2 plus so on and so forth plus cn yn is also a solution, where each of the c's is a constant. So we're going to look at the proof only for the case of the second order. So a2 of x d squared y dx squared plus a1 of x dy dx plus a0 of x y is equal to 0. Remember, we're considering homogeneous. The proof for the higher order is analogous. Well, we're going to let L denote the operator a2 of x d squared plus a1 of x d plus a0 of x. Then we can rewrite our differential equation as this. a2 of x d squared plus a1 of x d plus a0 of x, and then all of that y is equal to 0. Sorry. But this piece here is L. So this is just L of y, and that is equal to 0. Now we suppose we have two solutions, y1 and y2. So their solutions to L of y is equal to 0. Now let's look at L of c1y1 plus c2y2. Well, this is equal to c1 L of y1 plus c2 L of y2. And this step is using the constant multiple rule and the sum rule for derivatives that was learned in Calculus 1. Well, since y1 is a solution, to L of y equals 0, this term must be 0. Likewise, y2 is a solution, so this term must be 0. And so this whole thing equals 0, which is what we desired. So we can therefore conclude that c1 y1 plus c2 y2 is also a solution to L of y is equal to 0. And that completes the proof for the second order case. As was mentioned, the proof for a more general higher order case is analogous to this. Now, let's suppose that we're given a set of functions f1 of x, f2 of x, so on and so forth, up through fn of x. Now we say that this set is linearly dependent. If there exists constants c1, c2, up through cn, such that they are not all 0, and c1 times f1 of x plus c2 times f2 of x plus so on and so forth through cn times fn of x is equal to 0 for every x in the interval. If a set of functions is not linearly dependent, then they are said to be linearly independent. Another way of saying this is the set of functions is linearly independent if the only solution to this is the trivial solution. That is, the only way this linear combination is 0 is if each of the constants is 0. So let's take a look at the set of functions. f1 of x is equal to sine squared of x. f2 of x is equal to cosine squared of x. f3 of x is equal to secant squared of x. And f4 of x is equal to tangent squared of x. Now, notice that sine squared plus cosine squared is equal to 1. Also notice that tan squared minus secant squared is equal to negative 1. So we can write 1 times f1 plus 1 times f2 plus negative 1 times f3 plus 1 times f4, and this is 0. Therefore, these are linearly dependent. Now, how can we determine whether a given set of functions is linearly independent or linearly dependent? Well, we do so by making use of a new value. So we suppose that each of the functions f1 through fn possesses at least n minus 1 derivatives. The determinant given by w of f1, f2 through fn, which is the determinant of the n by n matrix, f1, f2, fn, f prime of 1, f prime 2, fn prime, fn minus 1, so the n minus first derivative of f1, the n minus 1 derivative of f2, and then the n minus 1 derivative of fn. This is called the Wronskian. Named after the Polish philosopher and mathematician Józef Maria Hołownia Wronski. I probably butchered that pronunciation. So we use the Wronskian to determine where a function, or I'm sorry, whether a set of functions is linearly independent. And we do so using the following theorem. So let y1, y2 up through yn be a set of functions then they are linearly independent on an interval I if and only if the Wronskian is not 0 for every x in the interval I. So to determine whether a set of functions is linearly independent, take the Wronskian. If that Wronskian is not 0 over an interval, then the functions are linearly independent over that same interval. Any set y1, y2 through yn of n linearly independent solutions of the nth order homogeneous linear differential equation on an interval I is a fundamental set of solutions or a fundamental solution set. Now, this is important because if we have a fundamental solution set, of a nth order homogeneous linear differential equation, on some interval, then the general solution is a linear combination of the fundamental set. So it's C1, Y1 plus C2, Y2 plus so on and so forth plus Cn, Yn, where the C's are arbitrary constants. We're going to prove this, again, only for the second order case. The general case is analogous. So we're going to let capital Y, let's make that more obvious to be a capital, be a solution, and Y1, Y2 be a fundamental set of solutions for the differential equation a2y double prime plus a1y prime plus a naught y is equal to 0. We're also going to suppose that x equals t is a point in I for which the Wronskian of y1 of t, y2 of t is not equal to 0. And y of t is equal to k1, and y prime of t is equal to k2 for constants k1 and k2. We now examine the equations. Capital C1, y1 of t, plus capital C2, y2 of t is equal to k1, and capital C1, y1 prime of t, plus capital C2, y2 prime of t is equal to k2. It follows that we can determine C1, and C2 uniquely, provided that the determinant y1 of t, y2 of t, y1 prime of t, y2 prime of t is not equal to 0. However, this is simply the Wronskian of y1 t, y2 t, which we've already said is non-zero. And so we can find this C1 and C2. If we now define g of x to be C1 y1 of x plus C2 y2 of x, then g satisfies the differential equation by the superposition principle. Furthermore, g of x satisfies g of t equals k1 and g prime of t equals k2. This is by these two equations right here. Notice that y of x satisfies the same equation and conditions. Because the solution has to be unique, because the solution must be unique, y of x equals g of x, which is c1 y1 plus c2 y2, as desired. Now, the functions y1 equals e to the x, y2 equals e to the 2x, and y3 equals e to the 3x satisfy the equation y triple prime minus 6y double prime plus 11 y prime minus 6y is equal to 0. I'll leave it to you to verify this. We will verify that this forms a fundamental set of solutions on the set of real numbers, and then we'll find the general solution. So to verify that it forms a fundamental set of solutions, we have to calculate their Wronskian. So the first row of our matrix is just the set of functions. The second row is the set of their first derivatives. The third row is the set of their second derivatives. So we get e to the x times the determinant of 2e to the 2x, 3e to the 3x, 4e to the 2x, 9e to the 3x, minus e to the 2x times the determinant e to the x, 3e to the 3x, e to the x, 9e to the 3x, and finally e to the 3x times the determinant of e to the x, 2e to the 2x, e to the x, and 4e to the 2x. So we'll get e to the x times, take a look at this first determinant, 18e to the 6x minus 12e. Sorry, not 6x, 5x. Minus e to the 2x times, now take the determinant of the second matrix, so we get 9e to the 4x minus 3e to the 4x plus e to the 3x times the determinant of this final matrix, so we get 4e to the 3x minus 2e to the 3x. So we get e to the x times 6e to the 5x minus e to the 2x times 6e to the 4x plus e to the 3x times 2e to the 3x. So it's 6e to the 6x minus 6e to the 6x plus 2e to the 6x, which is 2e to the 6x. So the Wronskian is 2e to the 6x. Now, no matter what value of x you plug in to e to the 6x, it is impossible to get 0. So this cannot be 0 for any value of x in the real numbers. So this verifies that they are indeed a fundamental set. So they form a fundamental solution set. The general solution is y of x equals c1 e to the x plus c2 e to the 2x plus c3 e to the 3x, where each of the c's is just some number. So any function, let's call it y sub p, that is free of arbitrary parameters that satisfies the nth order non-homogeneous linear differential equation is said to be a particular solution of that equation. If we let y sub p be any particular solution of the nth order non-homogeneous linear differential equation on an interval I, and we let the set y1, y2 through yn be a fundamental solution set to the corresponding or the associated linear homogeneous equation, also on I. Then the general solution, help if I could spell, is y of x equals c1 y1 plus c2 y2 yada 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 plus cn yn plus that y sub p, where again each of the c's is an arbitrary constant. So this is interesting because what this implies is that if we're solving a non-homogeneous linear differential equation, the first thing we should do is solve the homogeneous. Then all we have to do is find any particular solution and add the two solutions together. We will see this in greater detail in future lessons. I am going to actually omit the proof of this theorem. Finally, we can call this linear combination here as y sub c of x, which is called the complementary function, which will allow us to write the general solution, y of x, as the complementary function plus the particular. This leads into the superposition principle for non-homogeneous. So we had the superposition for homogeneous. Now we have the superposition principle for non-homogeneous. So let yp1, yp2, up through ypk be k particular solutions of the non-homogeneous linear differential equation on an interval I. So we're going to suppose that y sub pi denotes the particular solution to the differential equation a sub n yn plus a sub n minus 1 yn minus 1 plus so on and so forth plus a1 y prime plus a naught y is equal to g sub I of x. where I can be any integer 1 to k. Then the summation of all these individual particular solutions is the particular solution of the equation a sub n nth derivative y plus a sub n minus 1 n minus 1 derivative y plus yada 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 plus a1 y prime plus a naught y is equal to g1 plus g2 plus yada 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 plus g sub k. So what this superposition principle is saying is if you have a non-homogeneous differential equation where what the differentials is equaling is a sum of functions, in this case k of them, then we can find k particular solutions, one corresponding to each of the individual g's, then just sum them up. And again, we will see this in greater detail in later lessons. Let us now consider the equation a2 of x y double prime plus a1 of x y prime plus a naught of x y is equal to 0. Let's suppose y1 denotes a non-trivial solution to this equation on the interval I. We now seek a y2. Such that y1, y2 form a fundamental solution set. If they are independent, then the ratio y2 to y1 is non-constant on the interval, i.e., that is, y2 of x over y1 of x is equal to some function u of x, which means that y2 of x is u of x times y1 of x. We can then determine the function u by substituting this y2 into the differential equation and then solving for u. So this method is known as the reduction of order because it transforms the linear second order into a linear first order. Let's look at this more in depth. We're going to first put the differential equation into standard form by dividing by a2. So we'll get y double prime plus p of x times y prime plus q of x times y is equal to 0. Furthermore, we shall suppose that y1 of x is not equal to 0 for all x in the interval. Now we define y to be u times y1. So it follows that we get y prime is u times y1 prime plus y1 times u prime, and then y double prime would be u y1 double prime plus 2 y1 prime u prime plus y1 times u double prime. If we substitute all of this in, then y double prime plus p of x y prime plus q of x y will become, with some algebra that I leave to you, u times y1 double prime plus p y1 prime plus qy1 plus y1 u double prime plus 2y1 prime plus p y1 times u prime is equal to 0. But this right here is 0 because y1 is a solution to the differential equation. And so what we get is y1 u double prime plus 2y1 prime plus py1 u prime is equal to 0, which we can rewrite as y1 w prime plus 2y1 prime plus py1 times w equals 0, where w was u prime. Now, this equation is both linear and separable. We will solve it using separation of variables. So we rewrite it, dw over w plus 2y1 prime over y1 dx plus p dx equals 0. This will give us the natural log of the absolute value of w y1 squared is equal to negative integral p dx plus a constant c, which is w y1 squared equals some constant e to the negative integral of p dx. Solve for w, then replace w with u prime and solve for u. Will give us u is equal to some constant, let's call it c2, times the integral of e to the negative integral p dx all over y1 squared dx plus some constant c3. We can now choose c2 to be 1 and c3 to be 0. Then the second solution, y2, would be y1 of x times the integral e to the negative integral p of x dx all over y1 squared of x dx. And this comes from the fact that y was equal to u times y1. So this is how we can form a second solution from a known solution. We will be making use of this in future lessons. So that concludes this lesson. I hope you've learned something, and we will see you in the next one.